Welcome to AI Paper Slop. Today, we are doing a deep dive into the source material from a 2026 release, The Hitchhiker's Guide to Agentic AI, From Foundations to Systems by Haggai Reutman. And look, if you're building AI right now, the absolute core insight you need to absorb immediately is that the bottleneck has shifted.
Oh, completely.
Yeah.
The era of just, brute forcing scaling laws by pumping training compute into massive models, that's over.
Right. The frontier is now inference compute and agentic orchestration. I mean, this paper essentially proves that if you bridge hardware-aware system designed like FlashAttention 4 and decoupled RLHF with algorithmic leaps like GRPO and emergent self-correction, we are finally crossing from basic pattern matching to genuine, verifiable agentic reasoning.
Yeah, it's a profound paradigm shift.
Yeah,
we spent the last few years totally obsessed with parameter count, right? But the data in this paper maps out a completely different battlefield. So we're going to look at the physical limits of the silicon that forced this change, how preference optimization had to be rewritten, and that wild, unprogrammed aha moment where models literally started correcting their own mistakes mid-thought.
Plus, we'll get into why Anthropic's simple loop design is actually beating all those complex multi-agent architectures in production right now.
Yeah, that part is fascinating.
But let's start down at the bare metal, because you can't really architect a reasoning agent if you don't understand why the GPU is choking in the first place, right? The physical bottleneck dictates the math.
It does. It always does.
So the paper traces this hardware-software coevolution through the lens of flash attention. And it is just wild how fast the goalposts move.
Oh, every single GPU generation fundamentally relocates the choke point. Like back in the A100 days, FlashAttention 1 and 2, those were born out of a pure memory bandwidth crisis.
Right, because we couldn't move data from the high bandwidth memory to the SRAM fast enough.
Exactly. Then the H100 arrives, and suddenly the bottleneck shifts to data movement efficiency. FlashAttention 3 had to adapt by using the Tensor Memory Accelerator, which basically lets the hardware manage asynchronous data copies.
And that was alongside warp specialization, right? Just to keep the compute units fed.
Right. But then, with the B200 Blackwell architecture, the script just flipped entirely.
Because the matrix multiplications got so insanely fast.
An absolute monster. The matmul on a B200 outpaces the auxiliary operations completely. So now, we are non-matmul compute limited.
Wow.
The GPU is literally just sitting there waiting on software-emulated exponentials and conditional rescaling, which are, the exact mathematical steps you need for the softmax operation and attention.
Which totally explains the shift to Qt DSL for FlashAttention 4. I mean, they stopped trying to write these massive, clunky C++ CTEs templates and just moved to a domain-specific language embedded right in Python.
Yeah, because you're essentially doing traffic control on the silicon itself at that point. Qt DSL compiles like 20 to 30 times faster than those old C++ templates.
Right.
But more importantly, it gives developers granular control over register allocation.
Because when your bottleneck is non-matmul compute, you cannot afford a single mismanaged register.
Exactly. You have to know exactly where your hardware is stumbling.
And that stumbling becomes impossible to ignore when you zoom out from a single kernel to a full RLHF training run. I mean, for a 70 billion parameter model, generation takes up 60 to 70% of the wall clock time.
It's brutal. That is a staggering amount of idle time for expensive silicon.
Right. And autoregressive decoding is the culprit there. You are generating one single token at a time, and for every token, you have to fetch the entire 140 gigabyte weight matrix from memory.
Yeah, the arithmetic intensity, the ratio of math ops to byte transfers is just abysmal compared to the training phase where you process massive batches in parallel.
Okay, let's unpack this for a second. Think of your GPU cluster like a high-end restaurant kitchen. Decoupling generation from training means you don't make the world-class chefs. So the training GPUs sit completely idle while the waiters, the generation GPUs, slowly carry food out one plate at a time.
That is a great analogy. That physical separation of labor is really the only viable way to scale now.
So how does the paper outline isolating those workloads?
Well, you dedicate a block of, say, 32 GPUs entirely to generation. They run continuous batching, use INTA quantization, all just to maximize memory bandwidth speed.
Okay.
And completely separate from that, you have a cluster of 8 GPUs doing nothing but scoring. They just run the reward models.
Right.
And finally, a pristine cluster of 32 GPUs running pure training, executing PPO updates with BF16 precision. And they all communicate through asynchronous queues and shared file systems.
Wait, hold on. If the waiters and chefs are in different rooms, there has to be a massive synchronization problem. The generation cluster is using a specific set of policy weights to produce responses, but the training cluster is actively updating those exact same weights.
Yeah, they are.
And the paper notes they only sync weights every 50 steps to save network bandwidth. Doesn't using weights that are 50 steps stale completely derail the RL math?
You'd think so, but the math actually flips that assumption on its head. For a 70 billion parameter model, a single optimization step only nudges the policy weights by about 0.1%.
Oh, wow, that's small.
Yeah, so over a 50-step window, you're really only looking at roughly a 5% cumulative drift between the generation weights and the training weights.
Ah, I see. And because algorithms like PPO use a clipping function anyway, that drift just gets swallowed up.
Exactly. The clipping range in PPO is explicitly designed to handle probability ratio deviations up to 20%. A 5% drift doesn't even trigger the guardrails.
That's wild.
Empirically, syncing every 50 steps causes less than a 2% drop in the model's win rates. But it saves you from pushing 140 gigabytes of weights across your network fabric 50 times over. It is a massive win for throughput.
Here's where it gets really interesting, though, because decoupling the clusters solves the idle time for the chefs, but the waiters themselves, those 32-generation GPUs, are still moving slowly because of that autoregressive memory bottleneck.
Right. The generation bottleneck is still there.
So to fix that generation speed, the paper points to a purely algorithmic trick at inference time, speculative decoding.
Yeah, speculative decoding tackles the token-by-token bottleneck brilliantly. Instead of forcing the massive 70B target model to generate every single token one by one, you introduce a tiny, ultra-fast draft model, like a 1B parameter model.
Okay, so a much smaller model.
Right, and this draft model rapidly guesses the next K tokens. Let's say it drafts 5 tokens in a row. Then, your 70B model takes those 5 drafted tokens and verifies all of them simultaneously in a single parallel forward pass.
Wait, so does the draft model dilute the smartness of the 70B model at all? Like if the 1B model hallucinates total garbage for token number 3, do we just lose speed or do we lose quality?
You only lose speed. The mathematical guarantee of rejection sampling ensures 0 quality loss.
Really? 0?
0. The acceptance and rejection scheme guarantees that the final output distribution is mathematically identical to what the 70B model would have produced entirely on its own.
Huh.
If the draft model hallucinates on token 3, the 70B model keeps tokens 1 and 2, rejects 3 through 5, and then computes the correct third token itself.
So you just fall back to standard generation speed for that exact moment?
Exactly. But on average, you get 3 to 4 tokens accepted per verification step. That yields a 2 to 3 times speed up overall.
And when you layer that on top of VLLM and page attention, the efficiency gains just compound even further. Let's look at memory fragmentation, because traditionally, LLM routing was like reserving an entire restaurant for a party of 20, even if only 2 people show up.
Yeah, that internal fragmentation was a nightmare for the KV cache. Systems would pre-allocate huge, contiguous blocks of memory for the maximum possible sequence length of a prompt.
Even if the prompt was super short.
Exactly. Up to 80% of that memory was just sitting empty. Page attention solves this by treating the KV cache exactly like an operating system treats virtual memory. It breaks the cache into small, non-contiguous blocks, or pages.
So you only allocate the memory you actually need exactly when you need it.
It eradicates the waste. And because you are suddenly saving 60 to 80% of your memory, you can fit massive batch sizes into your generation cluster. You can run continuous batching, dynamically swapping user requests in and out at the token level without waiting for the longest sequence in the batch to finish.
Okay, so we've optimized the bare metal, we've bypassed the memory bottlenecks, and we've physically separated the clusters. We finally have the raw throughput required to train reasoning models at scale.
We do.
But as the paper details, the moment you try to scale up standard RLHF algorithms like DPO or standard PPO, the math starts breaking down under the weight of these reasoning tasks.
Yeah, it breaks down hard. I mean, direct preference optimization, or DPO, was a huge breakthrough because it completely bypassed the need for a separate reward model. It optimized the policy directly from offline preference data.
Right.
But when we want models to learn complex, multi-step reasoning, they need to explore dynamically. They need online reinforcement learning. Standard PPO allows for that exploration, but it requires loading an entirely separate massive value model into memory just to compute the advantages of a given action.
Which brings us to the elegance of GRPO group relative policy optimization, because it completely deletes the value model.
By using the group itself as the baseline, instead of comparing a single generated response to an abstract baseline predicted by some memory hogging value model, GRPO takes the prompt and generates a group of key different responses. Then it scores all of them using a lightweight reward rule, calculates the mean and standard deviation of those scores, and normalizes the advantages within that specific group.
So I have to ask, what happens if the entire group of K outputs generated by the model is just absolutely terrible? Does the least terrible output just get a massively positive advantage and get reinforced?
That vulnerability is exactly why RL requires thousands of steps.
Right.
Yes, if the whole group is bad, the least bad one gets reinforced. But the model's policy is slowly shifting.
Right.
Over time, it is constantly being pushed toward the higher end of its current capability distribution.
Yeah.
However, GRPO does run into a much more fatal flaw called the multi-reward collapse problem.
Oh, because in the real world, we aren't just scoring for one metric. We want the Python code to compile perfectly, which is one reward, but we also want it formatted beautifully in Markdown, which is a second reward.
Exactly. And the variance between those rewards creates chaos. Think of the correctness reward for a math problem. It's usually binary 0 or 1. You got it right or wrong.
Right.
But the formatting reward might be a smooth, continuous score from 0 to 1 based on syntax. In standard GRPO, if you just sum those rewards before normalizing, the reward with the higher variance completely dominates the gradient.
It's like trying to teach a dog to fetch a ball and also to bark softly. If you reward the fetch with a giant steak and the soft bark with a tiny pat on the head, the dog entirely forgets about the bark because the steak signal is just too loud in its brain.
That is exactly what happens. The lower variance reward experiences advantage collapse. It contributes almost zero gradient, so the model entirely forgets to optimize for it.
So how do they fix it?
The paper highlights GDPO, or Group Reward Decoupled Policy Optimization. You normalize each reward independently within the group before aggregating them. But the ScaleRL findings push this even further for language models.
Right, the introduction of CISPO, Clipped IS Policy Optimization.
Yeah. The ScaleRL researchers ran massive systematic studies on what actually makes RL scale. They found that if you only apply batch-level reward scaling, the improvements plateau. If you only apply token-level loss, again, marginal gains.
But you put them together.
When you combine batch-level reward scaling with token-level loss, they are uniquely synergistic. The batch scaling reduces the overall variance, while the token-level loss provides incredibly precise credit assignment for exactly which token led to the reward. CISPO proves this combination unlocks massive performance at scale.
So if we take all this, the flash attention for, the decoupled generation, the CISPO mathematics, and we unleash it on hard math and coding tasks, what actually happens to the model's behavior? Because this is where researchers notice something completely unprogrammed that just changes everything.
This is the critical aha moment, documented by DeepSeek during the RL training of their reasoning models. At a certain point in the training process, the models spontaneously started to reconsider their own initial approaches mid-chain.
Spontaneously.
Yes. They would literally generate tokens like, wait, let me reconsider, or actually looking at this again, I think I made an error.
And to be abundantly clear, nobody explicitly programmed them to say that. That text wasn't in some supervised fine-tuning data set that they were just parroting.
Not at all. It was pure emergent metacognition. It emerged solely from the RL objective of maximizing the final answer accuracy.
Right, it's incredible.
The model mathematically discovered, entirely on its own, that verifying its own work mid-stride yielded a higher final reward than just blindly continuing down a flawed path.
Which basically proves that instead of building a massive brain that knows everything instantly, which requires impossible amounts of training compute, we're taking a smaller brain and giving it a massive scratch pad and just a lot of time to work it out at test time.
That observation forms the exact foundation of the compute equivalence principle. We saw this popularized by the 01, 03, and 04 mini models. Traditionally, the only lever we had to pull was training compute. But reasoning models introduced test time compute. The paper shows a clear scaling law. More thinking tokens monotonically improve performance on hard reasoning tasks.
So training compute and inference compute are basically roughly substitutable.
Yeah, you can take a significantly smaller model, like an L4 mini, give it an extended thinking budget at inference time, and it will crush a much larger, massively expensive model that just answers instantly. The paradigm has shifted from massive model size to massive reasoning capability.
And if you're building products today, this changes everything. If models can now reason dynamically, self-correct, and take their time, forcing them into rigid, pre-planned architectures seems completely backward. Which brings us to how we actually deploy these agents, starting with a shift away from traditional RAG.
Yeah, traditional retrieval augmented generation acts as a rigid, blind pipeline. Before the model even starts generating a response, the system takes the user's query, searches a vector database, and stuffs the results into the prompt.
The decision of what to retrieve is locked in before any reasoning actually happens.
That's great.
Which is like a student trying to blindly grab all the reference books they might need for a final exam before they're even allowed to read the first question.
It severely limits the potential. The Search R1 paradigm flips this entirely. In Search R1, the decision to retrieve information is a learned behavior that happens during generation.
Okay, so how does that work in practice?
The model starts reasoning, hits a knowledge gap, and dynamically decides, I need to execute a search for this specific piece of data based on what I just figured out. Because the search queries are highly contextualized by the model's ongoing reasoning, this mid-generation search outperforms standard RE by 15 to 20% in accuracy.
Wow. And this ties directly into Anthropic's key insight for agentic architecture, because if you're currently building a complex 10-persona agent architecture where a coder agent debates a tester agent, Anthropic is basically telling you to rip all of that out.
They are.
Wait, so all the hype about building complex societies of 15 different agent personas debating each other, Anthropic is saying just give a smart reasoning model a simple while loop, good API access, and get out of its way.
Exactly that. The multi-agent orchestration trend was really just a crutch for models that couldn't reason well on their own. Anthropic's data shows the most effective agents are not complex hierarchies. They are simple loops.
It's a loop.
The code is literally, while not done, action equals model.decide, given context and tools. Execute the action, append the result, loop again.
The intelligence comes from the raw capability of the model and the clarity of the tools, not some elaborate multi-agent orchestration logic.
Right. A strong reasoning model with a simple loop and well-documented APIs will orchestrate its own problem-solving strategy far better than any brittle, hard-coded multi-agent hierarchy you could design.
But if we are just letting autonomous loops run wild with tools, we need mathematically rigorous ways to know if they were actually succeeding or just tricking the reward system, right? If you are an ML engineer listening to this, how do you evaluate these agentic loops in production?
Well, you have to bridge the gap between intrinsic and extrinsic evaluation. Intrinsic metrics evaluate the model in isolation, things like perplexity or BLEU scores. But a model with great perplexity might still be completely useless at resolving a complex GitHub issue.
Right.
We need extrinsic metrics, specifically task success rate, or TSR. Did the agent actually achieve the goal state?
And for coding and reasoning tasks, the gold standard metric that predicts that extrinsic success is pass at K. You ask the model to generate K different solutions to a problem, and you evaluate if at least one of them passes all the unit tests.
The paper provides a really critical diagnostic rule using pass at K. If your pass at 64 is less than 1.5 times your pass at 1, your model has absolutely no headroom for reinforcement learning.
Oh, wow. Why is that?
It means the model simply does not contain the latent knowledge to solve the problem. In that case, throwing expensive RL at it is just going to reinforce garbage. You have to go back and invest in better supervised fine-tuning data first.
If you are an ML engineer listening to this, and your team wants to throw expensive RL at a problem, check your pass at 64 first. But what if your pass at 1 is, say, 5%, and your pass at 64 is 60%?
Then you have the perfect candidate for RL. The model knows how to solve the problem. It just rarely navigates the probability space correctly on the first try. RL will teach it to consistently find that successful path.
Makes sense.
And when you evaluate the file system, you look at benchmarks like SW bench. That measures the percentage of real-world GitHub issues resolved by the agent generating a unified diff patch that passes every single repository test.
Which leaves us with a truly profound question to close this deep dive. We've talked about how small models, like O4 Mini, can punch way above their weight class through the distillation of reasoning. We know we can fine-tune small models on the generated thinking chains of big models, so they learn to imitate those strategies.
Right, the distillation process.
But when a small distilled model outputs a long chain of thought, is it genuinely reasoning? Or is it simply pattern matching the surface syntax and stylistic formatting of a reasoning chain? Are we actually distilling cognition or just imitating the shape of it?
That is the big question right now.
It's definitely something for you to mull over as you build your own systems. We highly encourage you to look at your current ML pipelines and see where these shifts apply, whether that's upgrading to Flash Attention 4, decoupling your generation clusters, or just stripping away complex agent hierarchies in favor of simple tool loops. Thank you for joining us, and we'll see you next time on AI Paper Slop.